In this lecture, we will see the most common equivalent models of BJT. Let's start with Ebers-Moll model. This model is used particularly for switching applications of BJT. And we know BJT operates in saturation and cutoff region while being used as a switch. It can also be applied for active region BJT, but its degree of accuracy reduces greatly. Consider an NPN BJT. You are aware of active region BJT where forward bias current of base emitter diode gets transferred to the reverse bias collector with ratio referred as active region common base current gain. This data can be represented in circuit form as shown. Similarly, in reverse active mode, majority of forward bias collector current gets transferred to the reverse bias emitter with ratio referred as reverse active common base current gain. The basic fundamental behind this model is that it superimposes these two modes of BJT. Like in saturation region BJT, as both junctions are forward biased, so both collector and emitter will be contributing currents to each other, and hence this mode emphasizes on the two junctions being called interactive junctions. From the diagram, emitter current plus base current plus collector current equal to 0. Let's number this equation to be first equation. Collector current is equal to forward active mode common base current gain into forward current flowing through emitter base diode minus reverse active mode current flowing through collector base diode. We know the value of forward and reverse current, and substituting the values we will get this expression for collector current. Let this equation be the second equation. Similarly, emitter current is equal to reverse active mode common base current gain into reverse active mode current flowing through collector base junction minus forward active mode current flowing through emitter base diode. Again, substituting the values of the currents, we will get the expression for emitter current. Let this equation be the third equation. These equations of collector and emitter current are the most basic equations on which Ebers-Moll model is based. It will be very complicated to derive the whole expression, but by using reciprocity theorem, we will find forward active mode common base current gain multiplied by reverse saturation current of emitter base diode is equal to reverse active mode common base current gain into reverse saturation current of collector base diode. In the previous lecture, we approximated the two reverse saturation currents to be equal for finding the standard equation of emitter current. But here we get the exact relation between the two reverse saturation currents. It is quite common in this subject that we have to change our approach to get the desired formulas. Another important characteristic of this model is collector to emitter saturation voltage, which can be written as base to emitter voltage minus base to collector voltage. By considering the first and third equation, we can have another equation for emitter current in terms of base and collector current. Let this equation be fourth equation. Now, by considering the fourth and the second equation, we will try to remove the exponential term containing base collector voltage to find the value of base to emitter voltage. Similarly, from these two equations, we can also find the value of base to collector voltage. Now we have both the values base emitter voltage and base to collector voltage. So we can get the value of collector to emitter saturation voltage. It will be better for you if you learn this formula, as it is not a very good idea to derive the relation in the exams. The chances of questions coming from this topic are very low, but not zero. Now we come to our next model, which is Gummel-Poon model. This model is particularly used when the base is non-uniformly doped. It is more advanced as it considers more phenomena like non-uniform base doping and can also consider early effect and high-level injections. Considering a BJT in non-equilibrium conditions, the magnetic carrier current density in base will be equal to the sum of diffusion and drift current density. Consider an NPN transistor with non-uniform base doping. We have already derived induced electric field to be equal to Boltzmann constant multiplied by temperature divided by magnitude of charge on an electron into 1 upon doping concentration of base, which is hole in our case, into gradient of hole concentration. After substituting the value of induced electric field, we will get this expression. Using differential equation basics, we find that the terms within the bracket can be modified to the gradient of hole concentration into free electron concentration. Therefore, the expression which we are left with is free electron current density into hole concentration divided by diffusion constant of free electrons into magnitude of charge on an electron to be equal to gradient of free electron concentration into hole concentration. Assuming diffusion constant and current density due to free electrons are constant throughout the base, we will integrate this equation to get this expression. This is the general expression valid for all regions of BJT. The denominator in this expression is known as base Gummel number. Even though we have considered non-uniform base doping, but the expression for base Gummel number is valid for uniform base doping as well. We can simplify this expression after considering few assumptions. The first assumption is low level injection. We have covered this topic, low level injection, in many lectures. In the unit of PN junction, when we were deriving the ideal diode current equation, we have considered low level injection. An example for your better understanding is represented on the screen. Suppose we have a p-type region with hole concentration 10 raised to the power 15 and free electron concentration 10 raised to the power 5. After biasing, the excess hole and electron concentration is equal to 10 raised to the power 6 per centimeter cube. To maintain charge neutrality, excess hole concentration is equal to excess free electron concentration. Now, the net hole concentration can be approximated to be equal to thermal equilibrium hole concentration, as the excess hole concentration is significantly small compared to hole equilibrium concentration. However, when we talk about free electron concentration, then we cannot ignore the excess free electron concentration, and such conditions are referred as low level injection, where the excess carrier concentration after biasing is comparable to minority carrier concentration, but it is significantly smaller than majority carrier concentration. If the excess carrier concentration is comparable to majority carrier concentration, then it will be referred as high level injection. Since we have a p-type BJT, therefore the hole concentration, which is the majority carrier concentration, can be approximated to thermal equilibrium hole concentration. And we also have formula relating net free electron concentration with thermal equilibrium free electron concentration and applied voltage. This formula we have already derived in the unit of PN junction and have used this equation in the derivation of ideal diode current equation. The second assumption, which is actually quite obvious, is we consider 100% ionization. Therefore, the majority carrier concentration, which is hole concentration, can be approximated to be equal to doping concentration of the base. And our third assumption, we assume the BJT is operating in active region. Therefore, the voltage across base to collector will be negative, which will lead to the value of free electron concentration at the collector junction to be approaching to 0. After applying all the assumptions and the approximated values in the expression, we will get this expression for free electron current density in the base. By mass action law, we also know thermal equilibrium free electron concentration multiplied by thermal equilibrium hole concentration is equal to square of intrinsic carrier concentration. Therefore, our final expression will come out like this. You can observe our base Gummel number has been modified to bring it in terms of doping concentration of the base. The Gummel-Poon model can also take into account non-ideal effects such as the early effect and high-level injection. If we consider the early effect, then as the base collector voltage changes, the neutral base width also changes so that the base Gummel number will also change. This change in base Gummel number with base collector voltage will make the electron current density given by the above equation a function of base collector voltage. if the base emitter voltage becomes too large, then the assumption of low level injection will no longer be valid. In this case, the total hole concentration in the base increases because of the increased excess hole concentration, which means the base Gummel number will increase. By similar analysis in the emitter, we can find minority carrier hole current density. In this case, the denominator is referred as emitter Gummel number. We can do the same analysis for uniformly doped base. We know the net free electron current density will be equal to drift current density plus diffusion current density. But here, electric field will be equal to 0. Therefore, net free electron current density will be equal to diffusion current density. We will first simply integrate it and we will assume all the three assumptions which we have considered in the case of non-uniformly doped base. And after using the mass action law, we can get the free electron current density. You can see the base Gummel number comes out to be equal to doping concentration of the base into base width. And if we have found the base Gummel number with the help of the expression which we got for non-uniformly doped base, then also we would get the same value of base Gummel number for uniformly doped base. One important point you have to keep in mind is that in Gummel-Poon model, minority carrier current is inversely proportional to total majority charge carrier. Now we come to our last model, hybrid pi model. This model is particularly used for BJTs which are used for amplification processes. All the parameters you have studied in PN junction will be used here. There is a very small resistance between the internal part of BJT to the actual terminal from where the output current is taken out of the BJT. This resistance is referred as terminal resistance, and we have three resistances for collector, base and emitter. In the unit of PN junction, we have seen that in a forward bias junction, we have diffusion and junction capacitance and diffusion resistance. Therefore, for forward biased base emitter diode, we have diffusion capacitance, junction capacitance and diffusion resistance. Also, we have studied in the second unit, for reverse bias junction, we have junction capacitance and junction resistance. And therefore, we have junction capacitance and resistance for reverse bias base collector junction. We also have output resistance, which we have covered in early effect. And we have dependent current source transconductance multiplied by internal base to emitter voltage. Transconductance of BJT is equal to collector current divided by thermal voltage. This dependent current source is the collector current in the transistor, which is controlled by the internal base emitter voltage. Here we have circuit diagrams for the components of the hybrid pi equivalent circuit. The first is between base and emitter, the second is between the collector and emitter, and the third is between the base and collector. If we combine all the components, then we will get the complete hybrid pi equivalent circuit. And this is a circuit which you are going to use a lot in analog electronics. However, in EDC, it may not be very useful. Now consider the case of low frequency or DC. For DC, all the capacitors will work as open circuit. Therefore, all capacitors will be removed. We also know that the terminal resistance's value ranges from 1 to 2 ohm. Therefore, we can also ignore the terminal resistances. The reverse biased base to collector depletion resistance is of the order of mega ohms. Therefore, we can also neglect the reverse bias base to collector depletion resistance, and the resultant circuit is referred as simplified hybrid pi equivalent circuit. When you will be studying analog electronics in initial units, you will be using particularly this model. As you will move towards high frequency circuits, then you will have to use the complete hybrid pi equivalent circuit. In some cases, you may have to ignore the output resistance as well. Now, this unit is finished. We will see latest gate questions in the next lecture. There are few channels which actually help you to understand the concept. Likewise, few years ago, I subscribed NISO Academy and NPTEL as they have helped me in understanding various concepts. However, presently I have turned off notifications as I am no longer a student. I have a small request from you. I don't compare my channel with such big channels, but if my lectures have helped you in understanding the concept, then please do subscribe.